So this video discusses about the electric potential energy and the electric potential. So what is the electric potential energy and what is the electric potential? So the understanding of these two things, and I should begin with the following concepts. We have two types of forces. We have what you call conservative forces and non-conservative forces. In the conservative forces, these are the forces that remains constant. And we have the gravitational force and also electrostatic force. These are examples of conservative forces. And while that of non-conservative forces, we have the forces like friction force, we have a spring force, and that sort of. Those are actually examples of non-conservative forces. So let's pay much attention on the conservative forces. And let's say we have an object. Let's say we have an object and which is somewhere up here. And let's say this is the ground. And let's say the object has to be released down from the up and are going to the ground. Let's say that is the case. And let's say this is the initial position in which the object is given as a child. And let's say this is the final position. I'll call it as HF. Let's say this is the final position given as HF. And let's say the object is of mass m in that way. So at this point, the object is at a point of high potential. It is at the region, I should say, it is at a point of high potential, where gravitational potential energy is greater compared to the ground level. So as the object is falling down, what is happening is that there is a decrease in the height. At the same point, there is a decrease in actually a gravitational potential energy. And as we are lifting it up, there is an increase in a gravitational potential energy. So how do we get it up to have the gravitational potential energy? We know that the work done is given as the force times distance. And let's say the object is moving vertically, and the force responsible, it is the gravitational force. Then the force of the object will be given as mg, like that. And since it is the vertical motion, and the distance will be given as the height. And now, what is this work done? So this work done, it is the work done due to the gravitational force, and that will be given as, that will be symbolized as u. That represents that it is a gravitational potential energy due to the gravitational force. And this gravitational potential energy depends on the mass of the object and also the height or the position of the object, of which g always remains constant. And for this case, we have the object falling, and which is of a constant mass. So which means what will only determine the gravitational potential energy, it is the change in height. That's what will happen. So which means as the object is falling down, there is a decrease in the gravitational potential energy. And as the object is going up, there is an increase in the gravitational potential energy. So keep that in mind. So let's now understand about, now we should also have to understand what is a change in actually gravitational potential energy. So which means we'll have final gravitational potential energy and the minus, and that is minus initial gravitational potential energy. So that is how the change in the gravitational potential energy will be calculated. So which means as the object is falling down, you will see that the final gravitational potential energy is less than the initial. Or have the negative gravitational potential energy. And as the object is moving up, there will be the positive change in the gravitational potential energy, since the initial will be less than the final as the object is moving up. And let's now see the concept of the work done on the object due to the gravitation active force. So you see that at all costs, as the object is falling down, work done by the gravitation force on the object is just simply given as mgh, and that is given as the positive because the object is moving in the direction of the gravitation force. And how about if the object is moving up? So the work done, so as the object is moving up, the work done on the object, actually the work done on the object by the gravitation force is given as the negative mgh. Is given as the negative mgh because the gravitation force is acting against the direction of the motion. So gravitation force always points downwards, but the object is moving upwards. That is in our opposite. So the work done on the object by the gravitation force is given as the negative mg. But you understand that having this case, it is the same as having negative work done is equal to mgh. That is the same as that, as you can see. And in this case, what it does is that for any conservative force, and for instance now we have a gravitation force, the change in potential energy, the change in gravitation potential energy, it is the same as the negative work done. So as the object is moving up, there is increase in gravitation potential energy. There is an increase in gravitation potential energy, but the work done on that particular object is given as negative, and that due to the gravitation force. As the object is falling down, you should have to understand that there is a positive work done by the gravitation force, since the object is moving towards the direction of the force. But now that positive work done, there is a positive work done by the gravitation force on the object, and hence the change in gravitation potential energy is negative because the object is losing height. So that particular change is negative. So we know that as it is falling down, the change in gravitation potential energy is negative, while the work done is given as the positive. But now having this case, it is the same as having the change in gravitation potential energy is given as the negative work done. So which is really making sense that in a general sense, and for the conservative forces, the change for the conservative forces, the change in gravitation potential energy, it just simply means it's just the same as having it as the negative work done. And this is true for only conservative forces. So keep that in mind. So now let's see on how we can relate the gravitational potential energy and also the electric potential energy. So keep in mind that we have the conservative forces, and that is gravitation force and also electrostatic force. So gravitation force and also electrostatic force. So much as we have the energy associated with gravitation force, that is gravitation potential energy, and also there has to be energy associated with the electric force. And what is that one? We call it as electric potential energy, that we can also be able to symbolize it as that. And since all these forces are conservative forces, so much as we have the gravitation potential energy due to the force of gravity, then we can also have electric potential energy due to the electric force. And since all these forces are conservative forces, Now the point of interest is, what is electric potential energy? Let's say we have a region of the uniform electric field. Let's say I should have it in this way. Let's say we have the region of uniform electric field and going down here. And let's say that is the case. But let me take it in this case. Let's say this is the case, and the region, it is of electric field given as that. And let's say we have a positive charge within the region. I'll call it as this. And it is at some point, let's say this is a point A. And now, since this is a positive charge, so always the positive charge feels the actually experiences the force towards the direction of the electric field lines. So this charge will experience the force towards this direction, and are given as Fe, and that much you know it has to be given as EQ. So that is the electric force the charge is going to experience within that region. But now instead, let's say the object happens to move up, let's say up to some point. I'll call it as, let's say, point B, and having some distance, I'll call it as given as t. Let's say this is the direction of the displacement in that case. So the object is moving from point A to point B, and against the direction of the gravitation, against the direction of the electric force, and which is acting on it. So if that's the case, then there is a work being done, and that work is due to the electric force. And what is that work? So that work is given as work is equal, and we know that the work is given as the force times distance. And now what is the force responsible? It is electric force. And what is the electric force? And by the way, that work is given as negative work because the object is moving against the direction of the force. So have negative work here. Should be, or have a negative there. And what is the force responsible? It is the force of gravity. Actually, it is the force of electric, and that corresponds to have it as a negative, EQ times the distance. So as the object, as the charge is moving up against the against the force of electric, then there is a negative work done on the charge due to the electric force. So this is how it will be. Now that is the work done on the charge by the electric field, actually by the electric force. Having this case, it is the same as having it as negative work done is equal the electric field times the charge times the distance. So by the way, electric force is also part of the conservative force. So having this case, it is also the same as having the change in electric potential energy is the same as the negative work done is the same as having, so it is the same as having electric field times charge times distance. And since electric force is also part of the conservative forces, so keep that in mind. So as the charge is moving from point A to point B, there is also change in electric potential energy, as you can see. And that particular electric potential energy can be a positive or negative. That change in electric potential energy can be positive, actually a change in electric potential energy, or can be a negative change in electric potential energy, as we talked about the gravitation potential energy being the energy change based on the a position of the falling object. We're going to also have the change in electric potential energy as the charge is moving from one place to the another. But now the point of interest is, what do you think will be the factors that will determine whether the electric potential energy can be a negative change or can be a positive change? What do you think are the factors that will determine the change in electric potential energy? Either can be a positive change or can be a negative change. Now let's consider the following case. Let's now consider the following case. Let's say we have the region of the uniform electric field in this case. And now we have, this is a charge within the region, and which is a positive charge. And I understand, let's say this is the point, I'll call it as a point A. And this is the electric field in that way. And let's say this is a point B. I'll call it in that way. And let's say this is the distance that we can have enough for the charge. Let's say in this case the charge will experience the force towards the towards down here, because it is a positive charge given as Fe. So if the charge is to move up here, there is a negative work due to the actually electric force. And by the way, you should be much familiarize yourselves with this expression. Change in electric potential energy is given as negative work done, and that is for all conservative forces. Now, as the positive charge is moving up, and it is moving against the direction of the actually electric force, then there is a negative work done on the charge, and due to this force. And now we'll have the change in electric potential energy being given as the negative times what is the work done due to the electric force. We'll have it as a negative work done. And for that case, we'll have electric potential energy being given as the positive work done. And this is true. So a positive charge, it corresponds to the change in electric potential energy as a positive. I should say the positive charge corresponds to the positive change in electric potential energy. So keep that in mind. So on the same case, even if we increase the magnitude of the charge itself, the change in electric potential energy will also be increased as well. Right. What if now we have a negative charge instead of a positive charge? What would you say? Let's say we have a negative charge given us that. And now the direction of the force will now change, will be upwards, because the negative charge experiences the force against the direction of the electric field. So hence the force will act up. That will be given as that. And now you will see that the electric potential energy will be given as, now since the force is acting along the direction of the motion, then there is a positive work done due to the electric force. And what will be that one? We'll have negative work. It should be a negative. So electric potential energy is given as the negative, and since the work is positive, we'll have it as times positive, and our electric potential energy will be given as the negative work. So now, for the negative charge, always it is more associated with a decrease in electric potential energy. So as you can see, electric potential energy, the change in electric potential energy is having two factors. One of the factors is the sign of the charge. So we have two factors that affect the change in electric potential energy. One of the factors is actually a sign of the charge. So she say sign. That is to say, a positive charge corresponds to the increase in electric potential energy, and the negative charge corresponds to the decrease in electric potential energy. And another factor, as you can see, it is the magnitude of the charge. So that is to say, if the magnitude of the charge increases, it means the electric potential energy will also be able to increase. And the magnitude, you should have to regard it as, let's say, you should have to regard it as the mass of an object. You know that if this is the object, we should know that the electric, actually say, if you should know that gravitational potential energy depends on the mass of the object and the height. So it is the same way you should have to expect for the electric potential energy on the context of the magnitude. So electric potential energy depends on the sign of the charge and the magnitude of the charge. So keep that in mind. Let's pay attention on the electric potential energy as well as the magnitude. How are these actually parameters are rated? So change in electric potential energy is directly proportional to the magnitude of the charge. Change in electric potential energy, it is directly proportional to the actual magnitude of the charge. Of course, it is also depends on the sign of the charge, as we have looked at actually, as we have already seen that one. But our interest is to have the relationship between the two parameters, and the relationship is direct. And now, for the moving charge, you know, if we have this is the charge moving in a uniform electric field, you know, amount of the charge, much as the magnitude of the charge is not changing, it means this charge is moving at a constant quantity. So which means amount of charge is not moving. So what do you think will be the factor? What do you think will be the factor for the change in electric potential energy? So the change in electric potential energy is equal to, now let's think of introducing a constant. The change in electric potential energy would depend on the change of that particular constant that we are to introduce, because for a particular charge, as it is moving, there's no change of the quantity of the charge. Like the same way as the object is moving, like the same way the object can move with some masses, with some masses, let's say we have the object of mass m moving towards this direction, you know, the mass of this actual object cannot change. Otherwise, we assume that the mass of this object remains constant. So if we assume that the mass of this object is constant for the whole entire journey, then whatever we're going to do, we'll consider the mass of the object to be constant. Right, the same way here, if we have the charge moving in a uniform electric field, if we assume that the mass, if we assume that the quantity or the magnitude of the charge is constant, then whatever we can do, you know, we'll still more have to stick to that assumption that the charge is of a constant quantity. So for this case, the change in electric potential will have to depend on the change of the constant we are going to have it here. And what is that constant? We have it as now the change in V determines the charge. And what is this delta V? It is what we call the electric potential. So electric potential is given as, you know, change in electric potential energy divided by the charge. So this is how we should have it. So which means the change in electric potential corresponds to the change in electric potential energy, and the changing itself, it is directly proportional. So the same way the electric potential can change, it is the same way electric potential energy can actually change. So what is the electric potential? So it is given as the change in electric potential energy by unit charge. That is what you call the electric potential. So as you can see the formula itself, electric potential energy is given in joules, and while the charge is given in actually a coulomb, so which means we'll have it as a charge, actually the energy, which is joules per coulomb. But electric potential, it is also given in volts, so which means 1 volts in that corresponds to the 1 actually joules per coulomb. So you see the basic unit of the electric potential being given in volts. It is the same analog there. So take note of that. So which means we can also have the electric potential energy. Should be electric potential can also be given as, apart from this expression, that is the change in electric potential energy divided by the charge. We can also have it as, a negative work done. Negative work done divided by the charge. So this is also another formula for the electric potential. So for a positive charge, let's now have an insight of the formula and have to understand what is happening. What you can have to understand is that for a positive charge, always the change in electric potential energy is positive. So which means, now for the positive charge, it corresponds to the positive change in electric potential energy. That is, if we have a positive charge here, if we have a positive charge here, it means the change in electric potential energy will also be positive. And also on the same case, the positive charge corresponds to the negative work done, as we have already seen that one. And how about if we have a negative charge? If we have a negative charge, and that corresponds to the negative change in electric potential energy, and that corresponds to the positive work done, as we have already seen that one before. So keep that in mind. So as the electric potential energy actually increases, it means the electric potential increases in the same way. And as the work done on the charge also increases, it means the electric potential energy increases in the same way. And mind you, all these are happening because of how strong the electric force is acting on the particular charge. So that is how you should have to understand about the electric potential energy and also electric potential. So let's appreciate some of the questions associated with the concept. Now let's say we have this question in which says that how much weight does the electric field do in moving a charge? Now we have a negative charge, that is negative 7.1, and what is micro? Times 10 to the power negative 6 kilo. A charge from a ground to a point with electric potential difference, and that is the electric potential change in electric potential. It's a positive 5.6 volts. Should be 5.6 volts. What is the actual work done? We should have to understand that the change in electric potential, let me have it proper here. So the change in electric potential, that's to be V, is given as the negative work. I should say the change in electric potential is given as the negative work divided by the charge. So it should be divided by the charge. And now in this case we have a charge which is of negative, negative 1 point, and that is, we have a negative charge, by the way. Let me just have to put it there, as we have a negative charge which is given as that. And we have the change in electric potential, that is 56 volts. We'll have it here, and I need to find what is work done on that particular actual charge. But now, what do you expect? Of course, if you have to cancel this, will be the positives, and you expect that the work done will be the positive, since we multiply the positive number and the positive number as well. But what do you think will be the direction of the work done? Actually, so what do you think will be the work done? Will the work done be positive or negative? So in this case, you should have to expect that this is the negative charge, and always it has to move. And always it has to move in the direction of, against the direction of the electric active field. So in this case, electric field and basically are moving from the positive, I should say, are moving from the region of high potential to the region of lower potential. So which means the direction of the charge, let's say this is, this is the ground level, and this is a point of electric potential given as 56, positive 56. Now obviously this is the direction of the electric field lines, and from this point. Now since this is the negative charge from the ground, it has to move upwards. So which means there is a negative work being done by the electric, actually by the electric. There is a negative work done being done. There is a negative work being done by the electric field, since the charge is moving against the direction of the electric field. So we'll have negative work done, as we'll be multiplying these two parameters to solve for work done. Now let's say we have also this question as well. How much work does the electric field do in moving a proton from a point at a potential of 12 volts to a point of negative 30 volts? Now what is happening here is that since this is a positive charge, and it is moving, a positive charge moves towards the direction of the electric field, and of which we expect the work done by the electric field to be a positive work. That is okay. But now it is moving from the region of high potential to the region of lower potential, of which the change in electric potential is basically negative. So in that case we'll have a negative work done, because of the fact that it is moving from the region of high potential to the region of low potential. Anyway, we are being given initial potential, that is 12 volts, and that we have been given the final potential, that is negative 30 volts. So what is the change in electric potential? We'll have negative 30 volts minus 12 volts. Minus 12 volts. That will be given as negative 42 volts. That is the change in electric potential. And we know that the charge of the proton is given as 1.60 times 10 to the power negative 19. And it is a positive charge, and the proton has to move in the direction of the electric field, and of which we expect a positive work being done. Of course that is the true. But now, since it is moving from the region of lower potential to the region of, it is moving from the region of high potential to the region of lower potential, it means the work done will be negative. So of which the work done is giving us now the change in electric potential times the charge. So work done will express it as a positive, but now since the change in electric potential is negative, or have negative, what is that in times the charge? That would be that. So on the case of whether the work has to be negative or positive, and I wish to be much aware about this. Change in electric potential, we know it is given as the change in electric potential energy divided by the charge, which is equal to negative work done divided by the charge. Now, if it is a positive charge, let's say if it is a positive charge, automatically you should have to understand that the work done by the electric field on this charge is simply given as a positive work. It will just simply be expressed as a positive work if it is a positive charge. Now we're talking about the work done by the electric field on a positive charge, because I should say work done by the electric field in a positive charge, it will be given as a positive because the charge has to move in the direction of the electric field lines. So you automatically have to think about the work being a positive. But now the thing will be based on the change in the electric potential. If actually a charge is moving from lower potential to higher potential, it means the change in electric potential will be positive. If the charge is moving from region of high potential to the region of lower potential, it means the change in electric potential will be negative. So you see that the work by the electric field on the positive charge will be negative because of the change in electric potential. Depends on the direction of the charge, that is from lower potential to high potential or else. While if it is a negative charge, automatically you should have to understand that if it is a negative charge, a work done by the electric field on the negative charge, it is given as the negative. Automatically is given as the negative. You have a negative work done. There also has to be considered on the direction, whether it is moving from low potential to high or high potential to low. It also matters. So you should have to consider all these things. And also on the case of the change in the gravitational potential in electric potential energy, you should also have to look at that one as well. If there is a decrease, you have a negative here. If there is an increase in electric potential energy, you have a positive here. So that's how you should have to understand about actually the calculations behind the electric potential as well as the electric potential energy. Thank you.